Hi, I'm Yong Shen, and today I will be talking about question 1 of tutorial 2C. The question has a reaction of reactant A forming product R. Okay, so the reaction has the following result of the respective concentration of A within the 4 minutes, and it is carried out inside a batch reactor. So the question requires us to show that the reaction has a first order of kinetics, where the first order of kinetics means that the reaction has an overall rate of reaction of 1. Before we proceed to solve the problem, let us first talk about the overall rate of reaction, where we'll be giving an example of this stoichiometric equation of reactant A plus reactant B forming product R plus S. And since we are talking about rate of reaction, we will not care about the product, we will only talking about the reactants. So we have to know that the order of reaction with respect to A is denoted by this small letter A, and the order of reaction with respect to B is denoted by this small letter of B. So we can then derive on the overall order of reaction, which is denoted by N, is equivalent to A plus B. So the overall order of reaction is equivalent to the sum of order of reaction with respect to A and the order of reaction with respect to B. Okay. So now that we have an idea of the overall rate of reaction, now let's get back to the question where the reactant A forms the product R. So we know that the order of reaction with respect to A is this small a, and in this case we know that is equivalent to 1. And since there is no reactant B, we can then conclude that the overall rate of reaction is 1, which we have mentioned that when the overall rate of reaction is equal to 1, it means that the equation has a first order of kinetics, which then means that we have proven nothing. So now let's move on to the second part of the question, where the question wants to determine the value of the rate constant by using the integral method. So when we use the integral method, we have to use the rate equation and the batch reactor design equation. So it's 2. There are 2 equations you need. So now let us know more about the rate constant. What is the rate constant? Is actually denoted by the K, and this rate constant can be found inside the rate equation of this equation, where rate equation equal to rate constant times multiplied by the concentration of A to the power of the overall order of reaction, where the overall order of reaction we found that is equal to 1. Okay. And then we also need the design equation of the batch reactor, which is negative dCA over dt equal to the rate of reaction. So if you have been paying attention, we will then find out that actually you can sub the rate equation into the design equation. So yeah, so basically do this. Okay. So now we have to follow the step of the integral method, where first step is to assume the order of reaction. Okay. So but previously we already found that the overall rate of reaction is equivalent to 1. So we can actually sub the m equal to 1 into this equation. So it will become basically K multiplied by Ca. So we will be making use of this equation later on. So the second step for us is to derive the design equation of the batch reactor. So we'll be making of this equation, and we can further rearrange this equation into this equation. section. Okay, so for this section, by means of integral method, right, we will be doing some integration to this equation. So we will integrate this by adding in the integrate signs. Okay, then we will do the max. We will do the max and integrate this equation, and then we will get this. This is the third step of the integrate, where we rearrange the design equation into a straight line equation form. So this is the third step. We have to find the straight line form, which then we can make this into a straight line equation to become like this. This is the straight line equation form where y equal to ln CA, x equal to t, and the gradient m equal to negative k, and the y-intercept equal to ln CA naught. So now we have to plot a graph of the y-axis, this one and this one. So we have to plot a graph of ln CA to t. Okay, so in order to do that, we have to get the value of ln CA, which previously we only have CA and t. We need to find ln CA. So that means the fourth step is to tabulate the new data of the ln CA, which is here. Okay, find it here. So now we have this data. Now we have this data, we can then proceed on to plot ln CA versus time. So if the graph has a straight line, it means that the assumption which we made is the overall rate of reaction is equal to 1 is correct. And by means of straight line graph, we have to know that the value of the r square is near 1, which means our graph is correct. So we can make use of the graph, and the graph give us the gradient of negative 0.7044, and we all know that the gradient m is equivalent to the negative k, and that means we can conclude that the rate constant k is equivalent to 0.7044. Here's our answer. Thank you.